Okay, so my keynote lecture emanates from my 40 years of experience in design-build solutions. It is geared towards the youth and students from the lessons learned, so I have some philosophical information and some lessons learned. I hope the experts and professors don't get bored. We'll see. I will start by telling you that this is a Buchanan lecture. It's an award given by Texas A&M honoring Spencer Buchanan. And the first Buchanan lecturer was Ralph Peck. Here I took a picture with him when I was a student and he was the first lecturer. So now after 30 years, I am as old as him, maybe a little younger. If you want to talk, come take my place. Yes, I don't have a problem. Maybe one day. So my presentation is divided in 4 chapters. I'm given 35 minutes. I may take a few minutes extra since we're already late. I'll start with the marriage philosophy, 4 chapters. With the units, everybody thinks units are fine. It's in mathematics, but in engineering, units are crazy. I saw in the presentation 33 feet. So some countries still use feet instead of meters. Believe me, 10 milliliters of antibiotics can save your children's life. This is a long time ago, my kids. But if you remove the M from milliliters, you can kill an elephant. So what I'm saying is 10 liters can kill an elephant. And this not only in geotechnical engineering. If you take the top scientists, engineers, NASA, in 1999, they lost the first orbiter that was supposed to take pictures around Mars. And that the problem was between pounds and newtons. And the worst thing is that everyone was amazed I didn't catch it. When you think also in aviation, there's a famous documentary, I recommend you watch it. It's Canada Flight 143. The way they lost power with both engines and the way he landed, it's all because of difference with units. About 50% of the forensics cases, 50% where I go and try to evaluate, I find a mistake somewhere with the units. So safety factor is important, 2, 3, but 10 is more important. Don't forget the units. I jump to intuition. Never ever use intuition when you're doing engineering. So if I ask you now, I'm going to throw a rope, the red rope, around the earth and come back to Nepal and tighten it. This is the perimeter, red. And then I ask you, this rope, we make it 6 meters longer from here to the wall and equally spaced around the earth. What is delta R? How high will it go? Will it rise? Intuition tells us it's negligible, right? But if you go back to simplest math in elementary school and back to marrying theory to practice, you will find that it will rise 1 meter. 6 meters will rise 1 meter around the earth. And it's independent of the radius. It can be a football. So never use intuition unless it becomes experience. So now next time somebody asks you this question, you will immediately say 1 meter. There's a difference between intuition and experience. If you heard of the trick of the page that you bend 50 times, you can answer this question. How thick will it be, the paper, if I bend it 1 time, 2 times, 3, 4, 10 centimeter, intuition, 1 meter, or much more? You're talking 225 million kilometers. If you can bend it 50 times. So you will reach the moon and keep going. So intuition, it's a no-no unless it becomes experience. Always revert back to theory. SOLGE is a principle I like to talk about. Collect the soil before answering any question. Show me the soil data. Did you take water level? Where is the piezometer? Clay, sand, rock. Look for all that. But also, what is the load you expect? Earthquake, lateral, vertical, cyclic. And call the architect. Talk to the architect, get the geometry, the civil engineer, the loads, and very important, the history. History, did you have any failure in nearby projects? Did they have a landslide last year, etc.? So SOLGE, you collect all the soil and all the data before you answer and try to always visit the site. See what is the mode of failure you expect, what's the applicable theory before you jump onto Plexus or any other software. So what I'm preaching is to think, because as engineers we have to satisfy this stable stool, like Morgenstern used the word stool, where safety and cost and functionality come together. What do I mean? Anybody can build a bridge, but the bridge will either collapse or will cost 10 times more. That's why we are engineers. We bring this functionality together. So what I'm preaching is run sophisticated thinking prior to sophisticated analysis, and use as much data as possible and latest technology, of course, like 3D finite element, BIM and digital twin systems, 3D visualization that geologists love these days, drone mapping, remote sensing, AI technologies. Of course, all of that should support your thinking before you do a judgment and take decisions. Never forget, we had equations that changed our life. I have two in my life that changed my career. I will show them in my case histories, but first I need to drink. If you see, engineering life is here slightly. It means the observational method. As you are living your life, you should think engineering. Like, as I'm drinking, I can test centrifugal force. I can test even. This one needs some prayers. Where is the flame? If atmospheric pressure exists, this glass can be 10 meters high, 10 meters of water pressure. So keep engineering in your everyday life, because life will be more fun if you do that. Maybe one more trick. Friction. I need a dollar bill or Nepali. So they taught us that static friction is stronger than dynamic. But if you put some moisture and you flip with mechanical deformation, it may change your ideas. And I'm preaching this so that you do all the thinking before you answer quickly. And for example, when you apply, is the video working? Can you play the video? So you apply centrifugal force with dynamic friction, life will be more fun. Technical problem, but it's okay. No panic. There should be a small arrow in the bottom I cannot reach, but let's see if the trick works. No? We'll pass it. Well, I'm drifting with my M4 BMW. Let's keep going. Basic transportation geotechnics, the footing bearing capacity. If you do SOLGE So we're collecting soil load, geometry, and of course history. Where is the history? It's right behind them. You can detect that the pressure from male and female both are close to each other. Unless she is wearing high heels, you better not put your foot under that. I felt it in dancing. But looking at this, you immediately can tell that settlement is not related to force, but it's related to stress, for example. And using the most common or most famous equation in its simplest form, the Terzaghi equation, you can tell that the ultimate bearing capacity is less than the stress they are applying. So is this failure? Yes, it is failure. If the criterion is, I don't want to see any deformation. So it failed because you see deformation. But in real life, this is not the case. So you have to be careful. And then footing on sand surface, in reality, will sink and stop. This may not be the case in clay. I like the clay engineering, by the way, here, the sponsors. It's the first time I see all the time the sponsors happening. This is a good idea. Without them, we are not here. In clay, this is not the case. I'm continuing with further analysis. So if you think of the apparent cohesion or the suction, it's about on the sand that's not fully saturated and it's not fully dry. This is what keeps them walking easily. I'm sure many of you experience this. And notice now the high effect of suction, and now we are talking 0.44. So that's why it stopped. When they sink 1 centimeter in slightly wetted sand, no problem. And this is what we call concept on sensitivity analysis. And then you keep going and I say, well, I want to use the same equation but predict the settlement if they go on the dry side. And that's what we call the concept of reverse analysis. And you can detect with the simplest form, it's about 5 centimeters. So always simplify your problem and then jump to sophisticated analysis is my recommendation. Now, deep foundations, if you dig yourself or sink in the sand up to the knees, assuming the SPT is 8 and friction is about 2 tons per square meter on the micropile skin, and the question is, what is the force needed to pull you out of your misery? Can a friend come, grab you, and pull you up? We don't know. That's where you go to theory. But before the theory, I want to tell you my dad is an engineer since the 50s, and here he's on a project. One time, he got a phone call that the trench where he was installing those pipes collapsed. And he said, I'm coming, I'm rushing. There was no cell phone. And one of the backhoe excavator operator had his brother in the trench. So he turned, grabbed him with a rope, and tried to pull him out to save his brother. He was suffocating. But when he did that, he didn't know that the force needed to pull his brother out is about 10 times his weight. And he killed his brother. So it's not a joke to go back to theory. This is a picture in Boston trench collapse, and you notice that they had to dig below the knees before they pull out with the special harness. So professional rescuers. Jumping to case histories now, second chapter. I don't know if I will have time because I see the clock 11 minutes. I will try to show you 3 cases related to sustainability. So the first one is Hilton implosion, is reuse of the same site to build a bigger, higher structure. The second one is a wind farm, renewable energy. And the third one is saving existing structures case. The Hilton is in Beirut, the Hilton project, so one. The second one in Texas, and the third one in Nigeria. I will go super fast. I am really sorry. This one is in Beirut. The Hilton project is here. The idea was to make this building collapse. I don't know if you can play the video now. Can we try? The Hilton, you don't see the basements, but my job was to maintain the basement walls in place while the entire building collapses using explosives. And everybody was happy to see the building down, except me. I was rushing to see if there are any cracks in the infrastructure around and the building nearby. The most problematic was collecting the load coming from the collapse and dynamically vibrating the earth and coming at the lateral acceleration. So what is the lateral acceleration I was expecting in my design for anchoring those walls? I had to go back to the theory using history of time domain, and from the time domain go back to Fourier transform, and using those Fourier transform, discrete Fourier transform from the time domain to go to the frequency domain and estimate the expected acceleration that we saw from a similar project. Historically, there was a similar implosion project in Beirut, and we determined the acceleration vertical lateral to use in our pseudodynamic analysis. Notice the deformation, keep it in mind. These are anchor forces. I will jump from anchor or global stability design, anchor design, in structural integrity design. You should see all of that. Pictures of implementing the anchors with high pressure grouting, and the head, special head with shock absorbent and redundant system for locking the wedges in place for those who install anchors. And finally, some photos before we saw the final product of 12-meter deep basements without the slabs, only with the anchors we installed in place, and I was relieved. Analysis, remember the curve in red? This is the theoretical prediction, but look at the one in magenta. This is the measured one, and there was a difference from plus 3 centimeters to minus 3 centimeters. And the anchors are here. You start asking yourself, what happened? And what happened is that the tower of the elevators did not crumble in pieces, but went down and hit the sides where the inclinometer was. So was this a bad design? The answer is no, because we designed for worst case scenario, and here it pushed, it's okay. So now you see the birth of the new Hyatt Regency and construction in Beirut. 7 minutes left. So between each case and the other, I will have a photo. This is the Jaita Caves in Lebanon. If you ever visit, it's one of the most beautiful in the world. I visited the Devi Falls, by the way. It's nice, but couldn't go enter no time for the cave. Wind farm in Texas, Sea Breeze. Project is 400 megawatts, 174 turbines, each 2.3 megawatts. Again, we collect the soil data with CPT, SPT. So we familiarize ourselves with the layers, the geometry. I'm simplifying here. It's one football field and 120-meter high turbine. The loads, summarizing the loads, vertical 162 tons and lateral 13 tons, exerting 1,600 ton-meter. If I remember right, it was at the emergency braking point. So the loads, what is the foundation we were asked we should use? Again, we go check the history. Remember, this is in the Gulf of Mexico, where you get surge waves because the farm is near the shore, and possibility of scour, so we had to opt for deep foundations. Then came the problem of cyclic loading. Yes, so the layout of the group was as such, 2 circles. We had to go back to theory of lateral static loads. Remember that we check L0 versus the length of embedment, and if it's L less than L0, the pile behave as rigid. If L is more than 3L0, the pile behave as flexible. But there is a missing link. So this was my PhD research, to link these two together with the dynamic equation. But before, I want to tell you the difference between flexible and rigid. Here I use a straw, and I cut a bottle, plastic bottle, and in sand, the same straw behaved as flexible pile. But when I went and bought mayonnaise and used the same micropile, you see the difference between rigid behavior and flexible. So same pile, but different soil will behave differently. You can also check that with your fingers. If you put a pile embedded in soil, the fingers is your finite element, and the pile embedded, if you put lateral load, if the pile bends or pushes your fingers, that's rigid behavior. But if I'm strong, I don't want to break the remote, I am strong. The remote will flex, the pile will flex because you are in rock. I will keep going. I like those simple tools. And tell you about the new theory of pile behavior under cyclic loading. If you develop the equation, which is this one, the 4th degree differential equation, and if you solve it, it was 2 years of work to solve it, and the result was beautiful. And if you type it in font 16, you get an equation that is 33 meters long in font 16. And I made my workers carry it so they know the importance of theory, not only execution, here on a deep excavation in Beirut. I'm sorry the video are not working, but you can see the flexural wave. I will skip the interaction to show soil structure interaction between the rigid theory and flexible theory, how the new theory collapses on the first one. If you go with small, because it's a dynamic theory, but if you put small, low frequency and you change the L, you can see how the new theory matches the old static theory, both in rigid. And so we solved the missing link, basically. Expected deformation and moments. Finally, sea breeze. I'm sorry I'm going fast. I will jump to the next case by showing you the Holy Kadisha Canyon in Lebanon. Many people don't know we have mountains and snow similar to here, not as high, but similar landslide problems and geohazards. Finally, the final one, I will go very fast, I have 2 minutes. This problem, I got there at the office of the owner, a major lawyer in Nigeria. He invited me to his office. I could immediately see cracks where I can put my hands in, not only in the walls, but in the beams. And he said, what do you think? How can we solve this problem? The building was sinking 1 millimeter per day. 1 millimeter per day. And I got there and I said, and he asked me, what should we do? I said, run. Let's run outside, finish the meeting outside, and then we will discuss further. Oh, really, really? And we went outside, and I asked him, immediately start unloading all the water tanks, chairs, tables, computers, everything you can. Only a few tons compared to the building weight. I'll tell you. You will see why. After I explain. And
yeah, sorry, because there was a mistake in the time, so you still have 10 minutes if you can just...
They made a mistake. They made it only 25 minutes.
Because I could see people, nobody is sleeping, so. I need to drink. I have time now. So, again, SOLJ, we collect soil data, geometry. This is where the micropile is. And when I got there, they were installing more micropiles. The foundation was on micropile groups. They were installing more micropiles to try to stop it, but the building was kept on going down, 1 millimeter per day, but not throughout. So they add a pile here, it goes down here, 1 millimeter. Then they stop this one, it goes down. So it was doing like this. And when I got there, I said, guys, you're doing all the effort of installing those micropiles, connecting them to the steel beams, and then the steel beams connecting to the columns. There is a problem here you're not seeing. What you're not seeing is that for the micropile to work, the building has to sink to activate the micropile. So the micropile would sink to grab power to resist up. What you should do is activate the micropile before connecting it. What do I mean by that? Unfortunately, the video is not working. So if we play the video, you will see how we jack hydraulically each micropile after installation against the steel beams. And I can show in the illustration. So we put the jack, lift or activate the micropile downward and push against the building. How much should we do it? Do you know till when should we keep pushing? Till the service load, ultimate load? You keep pushing until the micropile sinks all the way to give you the maximum power, and then you jump. Lock it, jump to the next one, jump to the next one. And after installing, I don't know if you can see, here is when I got, and it was still sinking. This is what we added, micropiles, and it stopped. The client was happy. I said, no, we need at least some 20% safety before I let you keep going. So we added about 40 micropiles, I think, for a total of 240. But what I want to show you here is after the building stopped from sinking with activating the micropiles, I started thinking. So from sinking to thinking, and I realized that the problem was miscommunication between the geotechnical designer and the structural engineer, between tons and kilonewtons, factor of 10. The geotechnical engineer didn't even look at the geometry, didn't even look at the units. It just, in kilonewtons, and he designed micropiles. The building is 5 floors, he put micropiles. Anyways, so the conclusion of this case, geotech, structural, architectural engineers, and all parties should communicate, should sit together, have lunch together, even dance together until the project is successful. Your ego should go last, should be last. And always don't forget to check the units. I have 5 more minutes, which is good. I'm very happy. I can show you the night sky over Mount Lebanon. Business as engineers, 3 small chapters here. Motivation, I like you to be in red. You're already in yellow for sure. In red, maybe. I can see some faces in red. Never be in the green, and I don't think any of you is in green. Temperature, you are in Nepal. So you can see all kinds of temperature, even in permafrost areas. But still be careful when you go work in hot deserts. So if you want to be international, you really should look at this map before you travel anywhere, even for tourism. I mean, even more so if you're going for work. This is another map of corruption. You are not bad. You're in the middle somewhere. You will have trouble if you want to work in Libya or even in America. Canada, worse. I mean, so what is the difference? Do you know the difference between these countries? One is done under the table, and one is an envelope with the mayor shaking hands over the table. We are all humans. This is a photo of Mount Lebanon. Some crazy skier. Finally, the conclusion. I have 4 minutes. I'm so happy. In conclusion, if you want to take a snapshot, collect data. Always collect data, SOLJ, before giving any answers. Always check the compatibility of units, and never ever give your answer before the units. Also, never ever give your answer based on intuition. Run sophisticated thinking prior to sophisticated analysis. Use as much theory as possible and advanced theories and methods and software. But after you do the sophisticated thinking, don't limit yourself to the code. The code is not made for all the problems, especially if it's a case where there is a failure. And innovate if needed, using what theory and experience taught you without ever compromising safety. So what you learn in class is very, very important. Visit the site, conduct monitoring, value engineering, long-term observation, call the client, visit the site again after 5 years. This is the best continuing education for yourself. And be ready to expand internationally with your business. Because I'm the president of the International Society, I have to tell you, be ready to go, especially now working online, you have to be ready to accommodate everywhere around the world. Finally, to connect with the theory of fundamental equation of geotech, Steve Jobs, before he died, he was giving a graduation speech, I think it was in Stanford. And I love this sentence. The only way to do great work. And I really love geotechnical engineering. Thank you very much.